Let's try lecture problem 12.2. It is important for the body to have the ability to cool itself. If not, even moderate exercise can be dangerous. Suppose a 70-kilogram man runs on a treadmill for 30 minutes using a metabolic power of 1,000 watts. Assume that all of this power goes to thermal energy in the body. If he couldn't perspire or otherwise cool his body, by how much would his body temperature rise during the exercise? Okay, so we're given the power, and we want to know how much his body is going to increase, or how much thermal energy is going to gain. And so the equation that relates thermal energy and power is just P is equal to Q over delta T. Heat over time. And so we're told that he puts out 1,000 watts. And we're trying to solve for this Q right here, right? We want to know how much heat is entering his body. And so all we have to do is rearrange this equation. Q is equal to P delta T. And we know delta T, we're told he does it for 30 minutes, and we know the power, which is 1,000 watts. So now I have to fill in here, so it's equal to 1,000 watts, or 1,000 joules per second, times delta T, which is 30 minutes, or, just keeping the same units, 30 minutes is the same thing as 1,800 seconds. So our seconds are going to cancel out, and we're just left with joules, and this comes out to 1.8 times 10 to the 6th joules. So that's how much heat or thermal energy that is going into his body. And we're told that he can't perspire or otherwise cool his body, so all of this is just going to go into heating his body. So if we remember the other equation for heat that relates specific heat of the body is, and like how much energy gain, is Q is equal to MC delta T, where this T now is temperature, or up here it was time. And so one thing we need to know before we go any further is the specific heat of the body, C. And we were told in the book, C is equal to roughly 3,400 joules per kilogram Kelvin. This is times. And so right now we're trying to solve for this delta T, right? We're asked how much was body temperature rise. And so we just rearrange this equation, divide both sides by M and C, and we're left with delta T is equal to Q over MC. And we know Q, which is 1.8 times 10 to the 6 joules, just this right here, over the mass of him, which is going to be 70 kilograms, times the specific heat of a human body, which is 3,400 joules per kilogram Kelvin. So let's make sure we're in the right units here. We have joules over joules, so the joules are going to cancel. We have kilograms over kilograms, so the kilograms are going to cancel, and we're just left with 1 over Kelvin. And so this is going to come out in Kelvin, and this is equal to 7.56 Kelvin. And since it's delta T, it's the same as Celsius, so 7.56 degrees Celsius. So if he couldn't sweat, his body temperature would rise quite a bit, and it would most likely kill him, actually. So that's lecture problem 12.2.